Okay, good day, everyone. I almost said good morning, but for most people here, it's not the morning anymore. So good day. Welcome to Drexel University's MXenes 10 years later virtual conference. Originally, we wanted this to be a conference where people came to Philadelphia, but it's not happening. This conference celebrates a decade really of scientific discoveries, innovations, and collaboration with industry and international excellence. And so over the course of the next 5 days, our conference is bringing together some of the best top researchers in the MXene field in all kinds of areas such as energy, storage, electromagnetic interference shielding, transparent conductors, water purification, etc. Today's topic is synthesis, structure, and properties of MXenes. My name is Michel Barsoum. I'm a distinguished professor of materials science and engineering at Drexel University. I am the chair of this conference and your moderator for today. And together with Professor Yuri Gogotsi, who's the co-chair, we would like to thank everybody listening and everybody contributing to this conference. It's going to be a great conference. Next, I would like to introduce our Dean of Drexel's College of Engineering and Distinguished Professor of Civil Architectural and Environmental Engineering, Dr. Sharon Walker. Please join me in welcoming Dr. Walker.
Thank you, Dr. Barsoum, and good morning or good Monday, everyone. It's my great honor and pleasure to welcome you, our leaders and guests from academia, the private sector, and government from around the globe to this very exciting event. While this is the fourth international gathering focused exclusively on MXenes, I'm thrilled that as the global leader for MXene research, Drexel's College of Engineering is host to the first such conference on US soil, or US servers anyway. It seems everything's connected to MXenes has the potential to be monumental, not only in terms of scientific discovery, but in terms of administrative lift. So on this latter point, my thanks go to all the staff and faculty who played a role in planning this significant event and in rapid response to the changes warranted by the COVID-19 pandemic, ultimately transitioning the conference for virtual delivery. This was no small task, and I'm indeed grateful for your dedication and your work in making this week a success. So thank you. As Dean of Drexel Engineering, I trust you'll allow me a few moments to express pride in the work of our material science and engineering faculty and student researchers as they exemplify what it means to be an engineer, what it means to be a Drexel Dragon. Nearly a decade ago in an interview, Dr. Yuri Gogotsi said, "The sky is really the limit, but it takes a lot of work, both modeling and experimental, to understand the properties." Now, of course, Dr. Gogotsi was referring to the then newly extraordinarily versatile family of two-dimensional materials, MXenes. Yet he captured the essence of what Drexel Engineering is about. We encourage our students and faculty to be innovative and to imagine without boundaries. In other words, the sky is the limit. We then guide and support them as they focus those big ideas to actionable outcomes, research contributions, industry applications, service to local, national, and global communities. And in other words, if you'll entertain another euphemism, it takes a lot of work to come back down to earth and hit the ground running. And running is truly analogous to the history of MXenes. Dr. Barsoum and Dr. Gogotsi discovered MXenes in 2010, and over the last decade, research has grown exponentially around the world. The materials were first reported in the journal Advanced Materials in August of 2011, after the process of using an acid etching liquid to chemically hollow out a layered material called max phases, which had been studied extensively in Dr. Barsoum's research group since '96, when he uncovered their extraordinary properties. This yielded a new type of chemically stable layered two-dimensional material. Called MXene, an amalgamation of its max phase precursor and chemical nomenclature, and pronounced MXene, Dr. Barsoom and Dr. Gagotsi discovered that using different kinds of max phases and different chemical etchants produced an entire family of materials wherein each member had unique properties. Early studies reported that the material possessed exceptional conductivity, which at the time made it an excellent candidate for use in energy storage devices like supercapacitors and batteries. Researchers have since revealed that in addition to their conductivity, MXenes are also physically durable and structurally versatile. In addition to energy storage, they're now being developed for a wide range of applications, including electromagnetic interference shielding, biofiltration, telecommunications, chemical sensing, and functional fabrics, and many other applications I'm sure we will learn about this week. As many of you realize, the discovery of a single new material would be considered a lifetime achievement by many. Yet within just the first 3 years, Drexel researchers discovered and tested a dozen different MXenes. Today, more than 30 different types of chemically distinct MXene materials and more than a dozen solid solutions of MXene have been isolated and are being studied. In addition, Drexel University has 47 issued patents and patent applications, which currently stand at various stages of prosecution in the US and abroad. This work represents the best that academia can give a world facing pervasive, relentless challenges. MXenes could be the key to building a smaller, faster electronics and improving energy storage devices, to providing clean water through advanced water desalination, to advancing technology for wearable electronics and the Internet of Things, and to providing advances in biomedicine for brain electrodes, wearable kidneys, and cancer treatments. This is translational research that has the potential to change lives. And so we gather virtually today and over the remaining course of this week. Remember that you are not witnessing history, but joining in history in the making. The presentations, conversations, research, and information covered in this extensive conference show just how far we've come in a short time, as well as how much remains to be done. This work will have a ripple effect that will continue to flow long after we part, and I, for one, am very excited for the future. In closing, I encourage you to visit Drexel Engineering's website, drexel.edu/engineering, for future information on MXene-related research and other news and events regarding not only our nanomaterials and material science, but all of our Drexel Engineering community. I thank you for your attention this morning, and I wish you a positive and productive conference experience. It is now my pleasure to introduce Dr. Alistair Saunders, Executive Vice Provost of Research and Innovation and Professor of Biology here at Drexel University. Alistair?
Thank you, Dean Walker. Good morning, good afternoon, good evening to all of you around the world. On behalf of Drexel University's President, John Fry, and our Provost, Paul Jensen, it's my pleasure to also welcome you to the MXene 2020 virtual conference. As the world struggles with the unprecedented challenges of the COVID-19 pandemic, the pandemic also creates opportunities. Virtual conferences like this one are able to engage many more participants than the participants at a traditional face-to-face conference. So for example, we have about 1,700 registrants for the MXene 2020 virtual conference. That's far more than the 400 we were expecting when the conference was a face-to-face conference. In addition, we've got far broader international participation, and the organization types that are involved are tremendous. In addition to that, participation, these virtual conferences also help to democratize information by lowering the barrier to information. We're gathered this week to share, to learn, and to envision new realities that MXenes might enable. The creation of new knowledge and the application of this new knowledge to solve challenges relies on partnerships. Bibliometric data demonstrates the power of partnerships. Citation impact measures clearly demonstrate that co-authored manuscripts with individuals from other organizations have more citations than publications from a single organization. When organizations are in different countries, the impact is even higher. Partnerships between companies and academics have the most impact in terms of citation impact measures. MXene research has spurred tremendous number of impactful partnerships between university research teams, between universities and companies, between universities and governments. Data from Drexel shows we've formed over 300 unique international partnerships in the past 5 years. And 50% of MXene publications are with international partners. We're so proud of these extensive and impactful international partnerships. With these partnerships, MXene technology seems primed to move into the marketplace. Startups will be critical in growing the impact and application of MXenes. To this end, partnerships between university startups and venture capital will be critical to maximizing the impact of MXenes. And these are new kinds of partnerships. To that end, my colleague Shintaro Kaido, the Vice Provost for Innovation and Director of Drexel's Applied Innovation, has organized a panel here at this conference on deep tech commercialization in venture capital. Panelists will include several venture capital funds with a track record of investing in university spinouts and transformational science. And it also includes leadership from the National Science Foundation. Please join Shintaro and the panel on Wednesday at noon Eastern Standard Time for that panel, and we hope you can participate. Finally, like Sharon, I too would like to thank my Drexel colleagues who worked so hard to transition this conference from a face-to-face format to the virtual format in a very short time frame. Specifically, I'd like to thank Danielle Capico, Gwen Grassberger, Christine Chang, Asia, and Mark, who are managing Zoom and the poster sessions, as well as Ryan, Max, and Andrew, who are helping manage other technical aspects of the conference. Without their hard work and the hard work of many others, we wouldn't be putting this conference on. So thank you all so much. And with that, it's my pleasure to welcome you to the MXene 2020 virtual conference. I hope that you'll consider joining us next summer for what we hope is a face-to-face conference here in Philadelphia. We would love to show you Drexel University, our College of Engineering, and our beautiful city. With that, I hope you enjoy MXenes 2020. And with that, I turn it back to Michelle Barsoom.
Yes, thank you, Alistair, and thank you, Dean Walker. Okay, what I have a couple of minutes now before the next, basically the starting of this conference. So I decided I want to take a few minutes and talk to you a little bit about the history of this MXenes and max phases, and also where we are and where we're going. So if we start, so everybody or most people know that MXenes are derived from the max phases, and so what I have here are 3 max phases. The max phases, when there's now about 150 of them. Anyway, when you etch the, so what you do is you start with a max, you etch out the A layer, and you end up with a 2D material. So you go from 3D to 2D. And what is absolutely remarkable is the ease by which you can do it. So if we take some titanium aluminum carbide, you can see here, and you put it in HF for 2 hours at room temperature, through the magic of chemistry, you go from 3D to 2D. It really is as simple as that. And this work, or the very first paper, was published in 2011. However, the actual discovery was made in 2010. So that's why we call this conference 10 years later. Anyway, so if I want to give you a very short and brief history of MXene. So this all started in the 60s by Nowotny and coworkers in Vienna. And they were crystal chemists, and it was a remarkable decade for Nowotny. They must have discovered 200, 300 new carbides, nitrides, and borides. And interestingly enough, titanium aluminum carbide was discovered by Schuster, also in Vienna, who was a student of Novotny. So the max phase that most people love, it was discovered also in Vienna. And then for about 20 years, nothing happened. And then early 90s, Pampusz and coworkers in Poland started trying to make titanium silicon carbide, and they came close, but their samples were not that clean. And then in 1996, our paper on titanium silicon carbide was published. And in that one, we showed that these materials really have remarkable properties. And in 1999, we discovered the first prototype of the 413. And that's when I decided to call these phases MAX phases or MAX phases. And then 2011, we discovered MXene here with Yuri Gugodzi and Michael Naguib. And then in 2014, so the first generation was HF etched, the second generation was non-HF etched, and that was important in terms of popularity of the material, as I'm going to discuss in a minute. Now, so what I think is remarkable is what happened since 2014 partially because of MXenes, and also just the field got a second wind. So in 2014, the magnetic max phases were discovered in Linköping University in Sweden. 2014 also, out of plane ordered 312, what we call OMAX phases, were discovered in Institute of Metal Research in Shenyang in China. In 2015, the very first 413 OMAX phase was discovered in University of Poitiers in Poitiers, France. In 2015, Babak and Asori and Yuri and I, we discovered the MXenes. Then in 2015, again, there was a AA max phase, gallium in this case, and this was discovered, interestingly, independently, both at Drexel Linköping. So the papers that came out have both institutions. And then in 2016, non-max phase MXenes in Ningbo, China were discovered. Qing Huang, Dr. Qing Huang is going to be talking about later. Also, the work in Linköping was with Johanna Rosen, who is opening the conference. And then in 2017, talk about Johanna, in plane ordered IMAX and IMXenes were discovered. 2017, the technology was licensed to Murata Corporation. 2018, molten salt max and MXenes were discovered in Ningbo, China. 2019, boron-based max phases were discovered in Tokyo Institute of Technology. And 2020, Yuri and his group discovered 514 phase, max phase, and its MXenes. And just last week, or a week before, a group in the University of Chicago used the molten salt technique to make superconducting MXenes and also change the terminations to a huge number, very large numbers. So, and the terminations essentially determine properties. So let's look at interest in MXene. So if you type MXene star in Web of Science on August 1st of 2020, you get 3,000 publications, 90,000 citation, index of 137, and average citation per paper of 28. What's as remarkable, if not more remarkable, is this exponential growth in papers per year. As you can see, they basically doubled every year since 2011. And in 2020, again, it's going to double again. The interest is absolutely tremendous. And if you look at the citations per year, again, last year it was 30,000. There was once upon a time where I could read all papers on MXenes and be on top of the field. These days are long gone. The other remarkable feature, and again, a measure of how interesting these materials are, the top 100 papers are highly cited. Okay, and so why is that? And I'll come to why in a minute, but I just want to show you here what I call MXene taxonomy, and you can make MXenes with just one element. You can make them with 2 elements. You can make them with 3, 4 elements that are not even on this chart. You can make MXenes where you have ordered vacancies. You can make MXenes where you have sandwiches. You can make also 413 MXenes, etc. And I didn't even add the 5,4. So, and this is just a small number of the potential possible MXenes. So there's absolutely no doubt in my mind that MXenes will be the largest family of 2D materials ever discovered by a long shot. And routinely there's a new MXene that's found every couple of months. And then this I took from Babak. So he put together a Max and MXene periodic table you can see here. And if we now add the science paper just alluded to, we can add selenium, I think, and tellurium. I mean, it's just amazing. You can have rare earth. So as you can see, almost the entire periodic table, with the exception of noble gases. So why are they so popular? And I think the reason they're so popular is, one, you get extraordinary properties with ease of processing. Okay, you can make 10, 15, 20 grams of the material readily in the lab. All you need is a beaker. It is really remarkable. And then the properties you get are amazing. And then what you get, and the main property, I guess, that distinguishes MXene is that you can think of them as conductive clays, you can think of them as 2-dimensional metals, and both of these did not exist before. So I think that's also very important. And then I just alluded to or showed you the large number of chemistries. So the potential is really, really, I mean, the sky's the limit, literally. And when you take the terminations into account, the number basically blows up, okay? Literally, I mean, it goes into the millions or billions. The permutations are just endless. And so I think that is very compelling and exciting. So for all the young people out there, it's still very, very early in the game. Extremely early in the game. So go ahead and start working on MXenes, and very simply, the future is very bright. All right. So the real heroes of this are my PhD students, at least the real heroes for me, who actually did the work. So Tamer Rakhi discovered the max phases with me in '96. Michael Naguib, you all know, in 2011, he discovered MXenes. Joe Halim did some very nice work on XPS of MXenes and other nice papers. Babak Nasori, who got his PhD with me, not working on MXenes, and then worked with Yuri, and is now a professor in Indianapolis. Michael Guidou with Boltzmann in the background. He is the guy who figured out to etch without HF. Michael, Carey, and Varun are currently doing some very nice work. And I like this picture from a few years ago because it has those 3 guys in it. And of course, you cannot discuss nobody can discuss MXene without talking about or mentioning Yuri. I think it's fair to say that Yuri is done more for the field than anybody out there. His output in quality and quantity is unbelievable. He's the hardest working person I know, and that's his group, I think 2019. So it's just slightly bigger than mine. I also like to thank Arman Mohammedi for doing much of the artwork towards the end. A huge thank you to our speakers. Here they are. And this row here, so these 6 speakers in one way or another have a relationship to Drexel. This is Mladen Radovic, who got his PhD with me many, many moons ago. And I already mentioned Michael Naguib is a professor now at Tulane. And Garrett Tucker is talking later today. He used to be at Drexel and now is in Colorado. And in terms of thank yous, I can't thank Drexel University enough. Dean Walker, Vice President Saunders, Gwen Grasberger, Christine Chang, Liz Poppard, and also Murata. I'd like to thank Murata for sponsoring this conference and also for sponsoring research here at Drexel. And I've been working with them closely for the past 3 or 4 years. Takashi Torito, Jerry Colby, Masashi Koyanagi, Akimura Yanagi Machi, Yusuko Gawa, and Tatsuya Matsugano. And in all of, in something like what we are doing now, there's always one person that just carries the ball. One person without which there would be no conference. And that person here is Danielle Cupico. She basically carried the conference, did 90% of the work, and it was a pleasure working with her. I hope to continue doing so for the next conference. Our sponsors are shown here, and the conference statistics, I'm not going to go through it, it's in your program, but we have roughly 2,000 participants, so that's the silver lining to the COVID pandemic. An in-person conference, you would never get to that number. All right, so, and today I have this, this is the program, as you can see here, for today. And so with that, I thank you again for your, for being here and for listening. And I am convinced we're going to have a fantastic conference. And originally we were going to have a 5-minute break, but it looks like that break is gone. So, but we will have five minutes between talks. So with that, I thank you. And I think we are almost ready to go to Johanna Rosen's talk.
Okay, then I think we're ready to go. So thank you very much, Michelle, for the introduction, and also thank you for inviting me to be part of this 10-year celebration of MXenes. Today I will talk about expanding the structural and elemental space of max faces and MXenes, and it will be a talk focused somewhat on fundamentals. So my background is slightly focused towards theory and modeling, but I have since the start been trying to split between theoretical work and experimental work. And this has led to the diverse group that I have today. And I would like to start by acknowledging this team. So we have the theoreticians in the first row. In the second and third row, we have people working on synthesis of nanomaterials, electrochemistry and catalysis. And here are people working on plasma-based material synthesis. And this is the team behind the results that I will present. But let's start by looking at the map of where we are today. I'm sure that many of you are familiar with this image, showing that in addition to traditional MXenes, we have chemically ordered MXenes. For the 2-1-1s, we have in-plane chemical ordering in the M layers. And for the 3-1-2 and 4-1-3, we have out-of-plane ordering with alternating M layers. In this image, gray represents the MXenes that have been predicted or experimental or investigated theoretically. And blue represents those that have been found experimentally. And as you can see quite many remains to be discovered. What the figure does not show is information on possible parent materials to the MXenes, if they exist or not. So today I will actually spend some time on the 3D laminates that we need to synthesize the 2D counterparts. I will just quickly go through some background and definitions so that it's easy to understand what we've done. So Gibbs free energy is defined as the enthalpy minus the temperature times the entropy. And this is the expression that we use to evaluate the phase stability, the theoretical phase stability of both known and hypothetical materials using density functional theory. In other words, we try to theoretically predict which materials are likely to be formed in synthesis experiments. For alloys, we also predict if we get a solid solution or chemical order disorder. To evaluate the phase stability, the most basic approach is to calculate the formation enthalpy of a phase relative to a set of most competing phases. If we take titanium aluminum carbide here as an example, it is based on titanium, aluminum, and carbon. Let's see, did I get a message now? Maybe not. Okay. Let's see. Yes, it's based on titanium. Let's see. So I hope I'm back in presentation mode now. Let's see. I need to check. So I cannot see my chat window now, but maybe someone can let me know if there's any problem with the presentation. Okay. So where were I? Let's go back to the correct slide. So if we take titanium aluminum carbide as an example here, as I said, it contains 3 different elements, and out of those we can form several different phases: single elements, binaries, and ternaries. And if we calculate the energy for titanium aluminum carbide and compare that to the energy of these phases or a linear combination of these phases, then we find that a linear combination of these two is actually a set of most competing phases, though they are not more stable than this one. So this one has a formation enthalpy of minus 27 millieV per atom, meaning that it is predicted to be stable. Let's see. But if we focus on the enthalpy, we assume that the temperature is 0, and for pure ternaries, 0 Kelvin calculations are actually quite useful. But if we investigate alloys, here you see an M element alloy, the effect of temperature becomes important. Not so much for vibrations, but for the contribution of entropy or disorder to Gibbs free energy. The entropy is defined based on this expression, where X is the alloy concentration on the sublattice that is alloyed. And by calculating the formation enthalpy of an alloy, and by including the entropy, we can actually estimate at what temperature we go from ordering at lower temperatures to disorder at higher temperatures. And this is what a chemically ordered configuration can look like. And when we have a result like this, we also calculate dynamical stability. In other words, how stable this structure is with respect to lattice vibrations. We also perform screening of structures, more than 1,000, to ensure that we indeed have the lowest energy structure for a certain stoichiometry. But let's start to talk about chemical ordering in max phases. Common for the 312 and 413 structures are the 2 crystallographic different M sites that we have. For 312, the first Wyckoff position is 4F. It is these red atoms here, also called M prime. And the second site is 2A. It is these green atoms here, or called MBs. Based on these two different sites, it is intuitively not surprising that we can get chemical ordering. And for an ideal OMAX phase, we have a 2:1 and a 2:2 ratio for these max phases. The first OMAX phase was chromium-2 titanium aluminum carbide, discovered by Liu and co-workers with out-of-plane ordering of the M elements. This was followed by more phases and also by corresponding 413 phases. The OMAX phases are of course interesting by themselves, but as important is the fact that they can be converted into corresponding MXenes with out-of-plane chemical ordering. The first example I show is the 312 OMAX, moly-2 scandium aluminum carbide. And you see this chemical ordering evident from the atomically resolved EDX here. And this is what the MXene look like. The second example is a 413, moly-2 titanium-2 aluminum carbide. And here you can actually see the chemical ordering in the max phase due to the Z contrast, which you can actually also see when it has been converted into a MXene. The first new study that I will present today, let's see where I am time-wise, is a theoretical study where we have looked into the origin of OMAX formation. So we have performed a theoretical screening of the phase stability and of chemical order disorder of the OMAX phases. We've used these M elements. We have looked at aluminium, since aluminium is prone to be etched and form a MXene, and we've used X equal to carbon. At first, we look at the stability of the pure ternaries, where the background color represents the stability. It should be white or more bluish if the material is predicted stable. And the square shows if the phase has been experimentally reported or not. And this is shown for 312 and 413. So, thermodynamically stable or close to stable max phases for 312 and 413 are found for M elements from group 4 and 5, while max phases from the group 3 and 6 are not stable. And all the experimentally known phases are indeed found in group 4 and 5. What is important to note is that the niobium 312 and the titanium, zirconium, and hafnium 413 are also predicted to be stable max phases, but are yet to be experimentally discovered. The trends in stability for both the 312 and 413 are similar to the trends found for the binary metal carbide in its rock salt structure, where M elements from group 4 and 5 are giving stable or close to stable carbides, whereas elements from group 3 to 6 give phases that are far from stable. And the comparable trends between these two can be related to the stacking of the metal and carbon in the metal carbide layers of the max phases, which is also found along the 111 direction of rock salt metal carbide. But now we go from the ternaries to quaternaries and possible OMAX formation for 312 phases, or what we can also call 2112 phases with a formula like this. This figure shows the results for different combinations of M prime and MBs, and the background color shows the formation enthalpy or the stability at 0 Kelvin. The symbol represents the atom configuration of lowest energy. If it is a black square, it is an OMAX, and if it is a round circle, it is a disordered max. If the symbol is surrounded by a square, it has been experimentally reported as OMAX if the square is green, and as a solid solution if the square is black. And experimentally known OMAX phases can be found down here. But as you can see, there are quite a few additional M elements that can form OMAX and that have a blue background. In other words, are predicted stable. But since typical bulk synthesis of max phases takes place maybe around 1500 Kelvin or 1500 Celsius or so, we need to consider the contribution from temperature and entropy, as I mentioned before. Including this, we see that many of the phases predicted chemically that are chemically ordered at 0 Kelvin are disordered at elevated temperatures. Still, a number of new OMAX phases seem to be stable. We have scandium with niobium, tantalum, and tungsten, and we have tungsten scandium and tungsten titanium. Another important observation is that the number of stable phases increase when we go from here to here. This is thanks to a large number of predicted new disordered phases represented by these circles. No squares means a lot of materials that remain to be realized. And interesting to note is also that, for example, niobium phases here, where niobium is actually not found is in the ternary max, but they are stable with niobium as the majority M element. So we do the same analysis for 413 alloys and possible OMAX, more precisely of a 2213 composition. The analysis, colors, and notation is the same as for the 312. In other words, we should look for squares with a bluish color, bluish background if we look for new OMAX. Here is the only perfectly sort of ordered OMAX that has been found to date, the Moly-2 titanium-2. But at 0 Kelvin, there are several more candidates. But again, if we increase the temperature, we see that many of the ordered phases turn into disordered one. But we also see suggestions for new interesting OMAX phases based on, let's see, tungsten, titanium, moly tantalum, and niobium hafnium. And this means that there are several here suggested OMAX phases that should be, that is just waiting to be discovered. So to summarize the work on the OMAX, I have suggested through the results that the compositional space of OMAX can be expanded, and also that the compositional space of disordered 312 and 413 can be very much expanded. What I haven't shown here is that we've made a more detailed analysis where we have compared the M element radius, the M element electronegativity, and also the M prime and A electronegativity. And the results show that for most known and predicted OMAX phases, the formation of OMAX is mainly governed by the M element next to the A layer not forming a binary rock salt metal carbide structure, and that the difference in electronegativity between M prime and aluminium being large. Most importantly, since we have here focused on aluminium-based OMAX, we suggest that by increasing the space of OMAX, we will increase the space of new 2D derivatives. In other words, we will get a range of new MXenes for further exploration. In the 2-on-1 phases, if I turn to those, there is only one crystallographic metal site, so out of plane ordering is not expected. Still, the max phase is hexagonal, so if we have an M element ratio of 2:1, we can actually form a honeycomb pattern of the majority metal in the M layer and have in-plane chemical order. This is what such order looks like if we have a top view of the M layer, and this is what it looks like in side view. But the energy for this structure, when not relaxed, is very high, so the phase is not stable. But the energy is drastically reduced if we allow an atomic size of the alloying element to be larger than the M element, and if we allow relaxation of the structure. If we start by relaxing the metal carbide layer and you look at the green atoms, you see that they will extend from the M layer towards the A layer. This, if you focus on this image, and if we allow the aluminium atoms to relax, will cause a rearrangement of the A elements. And this is what it looks like if we look in top view. And the resulting structure of the aluminium atoms is called a Kagome-like lattice. The first MAX phase that we discovered that had this in-plane chemical order was molyscandium aluminium carbide. It was actually discovered simultaneously when we grew thin films and when we did bulk synthesis. But for the bulk synthesis, what we did was we mixed elemental powders, we used pressureless sintering, and then when we look in the stem, we found a material which looked like a traditional MAX phase in the 100 direction, but which had two M elements which separated laterally if we looked in the other orientations. And from the stem and from the electron diffraction, we could conclude that we had a monoclinic phase as opposed to the hexagonal MAX phase. It didn't take too long before we had synthesized more of these in-plane ordered phases, and now we introduced the name IMAX for the in-plane ordered phases, and we also introduced the OMAX for the out-of-plane ordered phases to be able to distinguish between the two types. But what is important? What are the experimental signs of IMAX formation apart from composition? Well, as you can see in this stem image and in this schematic here, we have alternating intensity of the A element. So basically every second A atom is very weakly shown. We also have, as I mentioned before, one M element approaching the A layer. But since we maybe not do STEM on a routine basis, it's easier to do XRD. And there is actually one peak in the XRD scan, which is characteristic to the in-plane ordering. And it is this 110 peak around 19 degrees. There are 32 IMAX phases reported to date, that has A equal to aluminium and gallium, that has the majority M element of moly, chromium, tungsten, vanadium, and manganese, and the minority M elements are 14 different to date. Most of them have aluminium as A element, and many of them can actually be etched into MXene, but I will get back to that on the next slide. Since we've been working quite a lot on magnetic MAX phases in the past, we were eager to explore if we could incorporate magnetic elements into IMAX phases and to explore the magnetic properties. So we worked on rare earth-based IMAX of this formula. And here you see the lanthanides that we used, 11 of them. And here you see a schematic image of one of them. It's moly-terbium aluminium carbide, also shown here in the stem with atomically resolved EDX. If we look at the magnetism of these materials, most of them have a transition temperature below 20 Kelvin. And our studies to date, which also includes neutron scattering experiments, suggest that the magnetism is complex. But this is being further explored. And this is also what makes high throughput modeling or detailed modeling challenging. But if we get back to the MXene synthesis, several of these phases can actually be etched. But since they are based on moly as the majority element, we then tend to form the same type of MXene with no magnetic elements remaining after the etching. So if we summarize what we know about IMAX to date, it is that formation is mainly governed by a 2-to-1 ratio of the M elements. What I haven't shown today is that we've made a more detailed theoretical analysis. And this analysis suggests that in order to form IMAX, we should have a significantly different size of the two M metals. We should also have a preferably smaller size of A, and also the population of anti-bonding orbitals should be minimized, like for the OMAX phases. And using these guidelines, we foresee a widening of the elemental space for the family of IMAX phases, and we expect more phases to be synthesized. Again, and most importantly, is that since IMAX phases are parent materials for 2D MXenes, we also expect that the range of MXene compositions will be correspondingly expanded. Let's see. So from this point forward, I will focus on MXenes. Because what is interesting with IMAX phases is that if we etch them, we can remove aluminium like for traditional MXenes and then form a chemically ordered MXene, or we can get additional removal of the minority M element, leading to ordered vacancies looking like this. Here you see the corresponding TEM image. Yes, and the first vacancy MXene we synthesized was moly 1.33 carbon from the molyscandium aluminium carbide. Here you see an XRD of the max phase and the MXene formed after etching. Here is the multilayer, a schematic of the multilayer MXene after etching, and this is corresponding TEM image that is multilayers, but there is no aluminium remaining. And if we delaminate this multilayer MXene and then filter it to form a film and then make EDX, we can see that we remove from the max phase aluminium and scandium if we etch in HF or in lithium fluoride plus HCl. So both ways work. Here we see a low magnification image of a single flake with dimensions below 1 micron. Here is higher magnification with a fast Fourier transform of this image, and this reveals a hexagonal-based crystal with these chain-like features, which means that we have the ordered vacancies. And here is a more zoomed-in structure where we see this even more clearly. IMAX phases also enable selective elemental etching, or a concept that we've called targeted etching. And this means that from the same parent material, we can have either vacancy ordered MXene by removing aluminium and yttrium in this case, or we can just remove aluminium. And all these two scenarios are given by just using different etching procedures. Also, for the moly MXenes, we can study the effect of vacancies on the MXene properties, because we have the moly MXene from the IMAX, and we also have the moly 2 carbon MXene from etching of the moly 2 gallium 2 carbide. And if we compare these through theory and experiments, we can see from XPS and simulations, for example, that the vacancy MXene tend to have more F terminations. This could be due to that there are fewer electrons from moly available for bonding in the vacancy MXene, which then could suggest a preference for fluorine terminations. Resistivity measurements in linear 4-point probe geometry on 10 micron films, we see that there is a difference in 3 orders of magnitude, the resistivity of these two MXenes. Also, electrochemical performance in 1 molar of H2SO4 shows similar behavior as other MXenes, but for 2 millivolt per second, we have for the vacancy MXene around 1150 farad per centimeter cube. And for the moly-2 carbon, we have then a bit more than 700. The higher conductivity of the vacancy MXene is most likely a part of this result, but whether the vacancies increase the active sites and increase the fraction of the electrode accessible to the electrolyte, that needs to be further investigated. Yes, so we have also investigated vacancy MXene based on tungsten. And these results are part of another theoretical screening study where we evaluated the phase stability for tungsten-containing IMAX phases based on different A elements. And we found these two IMAX phases, and it turned out that both of them could be etched in either HF or lithium fluoride plus HCl, both realizing vacancy MXenes. This is what that MXene looked like in TEM, and guided by DFT calculations from the literature that predicted a high catalytic activity of a tungsten MXene, we decided to test for hydrogen evolution reaction. So to place these results in perspective, we compared the tungsten MXene to moly MXene and also to a platinum carbon electrode. So the results showed that the HER activity is best for the annealed tungsten MXene. But it should be stressed that these were our initial results, and we've worked on improving the MXene quality since then, which has improved the numbers for the unannealed tungsten MXene to above the tungsten annealed tungsten sample. But this is work in progress. So I tend to get back to the importance of MXene quality, which in my perspective is well-defined, homogeneous, reproducible material, of perhaps a rather low defect concentration. An IMAX synthesis to date has been based on elemental powders, but we're of course working on pathways for improving both the IMAX quality as well as the resulting MXene quality. And most studies to date on vacancy MXenes are on moly 1.33 carbon from the moly scandium aluminium carbide. And this has been motivated by the shown high potential for energy storage applications. As I mentioned before, the as-synthesized MXene when it was tested for the first time, it gave a capacitance of about 1150 farad per centimeter cube. This could be increased after annealing to more than 1600. We've also used the moly MXene in solid-state supercapacitors, mixed with P.PSS, and more recently we have formed composite electrodes with cellulose, where we've had a high MXene mass loading, and that has shown really good results. And we will continue to explore the moly MXene from moly scandium aluminium carbide. But in terms of cost, and therefore applicability, and so on, we have performed a project on tailored synthesis approach of moly yttrium aluminium carbide and its MXene. So as I mentioned before, we synthesized this IMAX from elemental powders before. This worked all right. The most important thing is to make sure that your yttrium is not too old, since it tends to oxidize. But still, what we could not get rid of is this secondary phase, which was more than 30% of the sample, even after optimization of the synthesis conditions. So now, in a new project, we've tried to use an aluminium yttrium alloy to suppress this secondary phase formation. And what we got was IMAX synthesis with a close to 80% sample purity. This secondary phase was reduced to just about 4 weight%. We got nice IMAX grain size, average of about 15 microns. And zooming in, we find a high quality also on the nanoscale with a confirmed structure of monoclinic symmetry. So to convert the IMAX into MXene, we previously used 10 weight% HF for 72 hours, and we got a MXene yield of 0.5 milligram per milliliter. For the new IMAX sample, we also used a new etching procedure. And for the same amount of starting material, we now have a MXene yield of 3 milligram per milliliter, which is 6 times higher than before. And as important, if you look at this STEM image, you see the well-defined MXene of high structural quality with the ripples or chain-like features that are characteristic of the ordered vacancies. It should also be stressed that this yield, 3 milligram per milliliter, is 3 times higher than what we get from the scandium-based IMAX phase. So if we now take our optimized MXene from molyyttrium IMAX, we can turn it into a highly flexible film without any additives. And here you also see a cross-section SEM. As expected, the XPS analysis show very similar surface terminations if we compare our old and new MXene synthesis approach. We also did some electrochemical analysis in 1 molar H2SO4, but I will not go into detail as the behavior is the same as our previous studies on the MXene. The capacitance is high, the stability is high, but what I want to stress is that if we compare our previous MXene with this new one, or with this optimized one, shown here in red diamonds, is that the new one is as good as or even better compared to the MXene from the scandium-based IMAX. So by starting with an aluminium yttrium alloy for the IMAX synthesis, and by optimizing the etching process, we've synthesized a MXene with matching or even improved yield, quality, and performance compared to the MXene from scandium-based IMAX. And altogether, this is important in terms of reduced waste material, use of more abundant elements, lower cost, and therefore higher applicability. The somewhat time-consuming MXene synthesis, I will just check my time. The somewhat time-consuming MXene synthesis that we are used to brings me to the last topic of today, which I've called an ultra-fast method for MXene synthesis. And I should mention that this is a collaboration with RMIT University in Melbourne and the group of Professor Leslie Yeo. So MXenes are, as you all know, typically synthesized by, quite often, time-consuming multi-step procedures involving a lot of chemicals. The first method was, as Michelle summarized in the introduction, HF etching. It was later followed by lithium fluoride and HCl, and more recently, other methods. But all the reported methods to date warrant the use of an acid at some stage in the synthesis process. We have most recently discovered that MXenes can be synthesized in a few milliseconds without the need for acids by using surface acoustic waves. So surface acoustic waves are 10 nanometer amplitude Rayleigh waves of a megahertz frequency, which are generated, confined to, and subsequently propagate along the surface of a single crystal piezoelectric substrate. And due to the very high surface acceleration and strong electromechanical coupling in the piezoelectric substrate, one can realize, for example, exfoliation of weakly bonded van der Waals compounds, such as molybdenum disulfide or tungsten disulfide. And this is what has inspired our related study on MXenes. This is what a device looks like schematically. It's maybe 1 times 1.5 centimeter. And this is what the device looks like in real life. Since one can exfoliate moly disulfide and tungsten disulfide, we start by just trying to use the same procedure for a max phase, titanium aluminum carbide. We have inserted the device here into a collection tube, and in here we have max phases in water, and droplets are then dispensed onto the substrate. The surface acoustic waves of a 30 megahertz frequency drives nebulization of the droplet into smaller aerosol droplets that are collected at the bottom of the tube. And if we analyze what we have collected, it is still max phase. In other words, the surface acoustic waves only is not enough to break the interlayer bonding of the max phase. The key is addition of lithium fluoride. In other words, if we have a max phase in water and lithium fluoride and then apply the surface acoustic waves, then the nebulized drops contain delaminated MXene flakes. How can this be explained? It has recently been shown that the electric field accompanying the surface acoustic waves can dissociate water molecules and generate hydroxyl free radicals and protons. And this, combined with our addition of lithium fluoride, generates what could be called localized in situ HF. In other words, local chemistry similar to what we would have if we would have used HF. And in line with traditional MXene etching, this etches away the aluminium in the max phase, and the mechanical vibrations from the surface acoustic waves facilitates the delamination into single flakes. If we turn to our experimental data, you see here XRD of the max phase here at the bottom, and XRD of a freestanding filtered MXene film obtained from this new method. The residual amount of lithium fluoride here can be removed by washing, then you get this XRD, but since we want to reduce the synthesis time and the number of steps, we focus on this one. So figure B therefore shows the MXene suspension after the one-step surface acoustic wave MXene synthesis and the resulting MXene electrode obtained after filtering. And here is also the cross-section. To evaluate and quantify the MXene surface terminations, we did XPS. The results show no aluminium as expected and a similar fluorine content compared to a traditional titanium MXene obtained from etching in lithium fluoride plus HCl. An important result is that an electrode like this for further characterization is obtained in just 40 minutes using one surface acoustic wave device. The MXene derivation is further confirmed by STEM. The low magnification image shows sheets of up to 1 micron, and B and C shows the lattice resolved hexagonal MXene structure with some vacancies that we are used to see. To demonstrate that this technique provides a material similar to what has been synthesized before, we produced an electrode for initial analysis with respect to electrochemical energy storage. I will not go into detail, but charging mechanism, measured volumetric capacitance, and also conductivity falls within the range reported previously for this material. So the new shown technique can be summarized as a salt solution-based acoustic MXene synthesis. But we expect that it can be used for MXene synthesis also when using other F-containing chemicals in the form of a dispersion solution for the max phase. Examples could be other salts like sodium or potassium fluoride or Lewis acids. In other words, the proton formation combined with the fluorine ions will form localized HF, which works as a local etchant for the MXene synthesis. The concentrations of chemicals can also likely be tuned so that the localized HF formed in situ is completely consumed in the process. What is important is that the process uses only salt, lithium fluoride, and water, which eliminates the use of harmful acids or bases. It's safe to handle because the solution only temporarily attains a pH value between 4 and 5 when the surface acoustic waves are used, and then it recovers to a value above 6 within minutes after we've stopped the surface acoustic waves. And finally, the procedure is fast. As I mentioned, synthesis of our electrode took 40 minutes using just one small device. And this time can of course be reduced with more devices used in parallel. And with this, I've reached the last part of my presentation, which is a very short outlook. And there is time for that. I return to the image that I started with, and I hope that the results I've shown have been able to convince you that many more 3D and 2D materials remain to be discovered, possibly also by using new synthesis methods, so that this figure will be even bigger and turn much more blue. I will end with a few examples of what I think lies ahead of us. So far, I've talked about chemical ordering of the M elements, but here is another example, which is substitution reaction in Moly2 gallium-2 carbide. So if we have a film of this material, we have gold as a capping layer, and then we heat it up, we remove almost all gallium and we get gold in there instead. But we get 9 gold to 1 gallium, which is chemically ordered in the A layer, as you can see here. This is not something that we have looked into at all. We discovered it more or less by accident, but this shows that many more phenomena, not only for the M element, concerning chemical ordering remains to be discovered. Another example is what happens if this is an Omax phase and this is an Imax phase. And my other example is to look into what happens if we mix the two. Then we get what we call an Oimax phase, which is actually a max phase with out-of-plane chemical ordering, but in the M layer closest to the aluminum layer, we actually also have in-plane chemical ordering. And for certain elemental combinations, for A equal to aluminium, a phase like this is very stable in theory. So this means that we strongly believe that these materials can be synthesized, and since they contain aluminium, we also suggest that their 2D derivatives exist. Let's see, and finally, see what time it is. Yes, finally, a last teaser, which shows a new beautiful MXenes, which also show that we maybe have only seen the starting point of in-plane ordering in MXenes. This is a 2D material based on a metal and carbon. This is a top view SEM of the MXene sheet. I need to acknowledge Professor Per Persson for this image. And what is very interesting is that it is the M elements that form a kagome-like pattern like this. And I think it is really beautiful. So I will jump past talking about thin film synthesis, and I will just summarize my talk by saying that a range of new Omax, Imax, and Oimax phases remain, and their 2D derivatives remains to be discovered and explored. And I finish my presentation by posing the question that I tend to pose in several conferences, because I think it is so important considering the huge number of both MAX and MXenes that are being discovered on a regular basis. And that is the question, what is the definition of a MAX phase and MXene? I look forward to a continued discussion on this topic later this week. And with this, I say thank you to the funding agencies that have enabled this research. And I also say thank you very much for listening.
Okay. All right. Am I live this time? And first of all, I want to profusely apologize. I was told after my talk that the slides did not show up. We had some kind of technical difficulties. My apologies. I am going to, in the 5-minute break, I will, if I can do that, I will share the slides with you just to show them to you. Again, my sincere apologies. Okay, thank you very much, Johanna, for a superb talk as usual. Your SAR results are really fascinating. And I have a few questions from the audience. And so I'm going to read them to you. So the first one is, do you think the SAW technique is safer than lithium fluoride HCl? In the sense that both create HF locally.
I think it is safer because since the method is based, since the critical part is the water splitting, and if we just wait for a short time, the hydroxyl and the proton will recombine, I think that it is safer because there will be basically no HF environment if we just wait for a few minutes after the process.
Okay. The other question was, what is the flake size distribution in your SAW technique, and how does it compare to other methods?
The image I showed was, I think it was like micrometer size of the MXene. What I should stress is that we have not worked a lot on optimizing. We have not tested different grain sizes of the max phase to start with. And we have also not optimized the amount of chemicals, the time for the time that we apply for the surface acoustic waves, and so on and so forth. So what I showed was micron size, but I think that we will be able to change this if we optimize the process.
Mm-hmm. Okay, it's somewhat counterintuitive because you'd think that the acoustic waves would shatter the flakes, but all right. Another question, we have time for a few more. What is the, so how scalable is it, do you think?
Yes, that is something we've been discussing because of course that's a very relevant question. You saw the size of these tiny devices and they are produced by conventional wafer scale photolithography. The power of one of these, it's just a few watts if you use them. So, I mean, you don't need a lot of energy. And I think they said that maybe one device is $1. So I think with time, I think it really has potential for parallelization, especially if we optimize the process further.
Okay, so now changing topics slightly, the question is, presence of vacancies show better properties. Does that apply to all MXenes or only the moly?
Well, that is something that we would like to be able to investigate in more detail, but unfortunately, the moly MXenes, they are the only ones where we can actually investigate that, because if we have a vacancy MXene, we need the counterpart without vacancies. And that does not exist, for example, for the tungsten material, right? The only tungsten-based MXene is the one with vacancies. So we have nothing to compare to, in a sense.
Okay, another question, related question is if you have more cation vacancies, if you can, I'm paraphrasing the question, if you can increase the vacancy concentration of the moly,
yes,
in your MXene, what do you think will the effect be on capacitance and stability?
The effect of the capacitance. I honestly do not know, since we do not know really why the vacancies give better results in the first place. What I can say is that the IMAX phase, and now I talk about the molybdenum aluminium carbide IMAX, and we try to alter the moly to scandium ratio so that we may form more vacancies. Then the MXene tend to be very quickly unstable. In other words, if we go away from the 2-to-1 ratio, we will not be able to form the MXene. So we cannot explore more vacancies in these materials as of what we've seen to this date.
Right. Another one also related to the moly MXene is, why is the vacancy containing moly more conductive?
Why is that? We don't know. The challenge is once again that the two different MXenes, the one with and the one without vacancies, they have different concentrations of surface terminations. And we all know that the surface terminations are also critical to the transport properties. So I think it is very difficult to say in detail what the vacancies themselves cause in terms of properties and not.
Okay, thank you, very good. So also, what is the effect of the vacancies on the termination and the overall chemistry?
Well, as I mentioned, the moly MXene, the vacancies tend to, if I talk about the moly MXene, the one with vacancies tend to have more fluorine terminations. And we suggest that that is due to the fact that we have less electrons available from the metal. So, and fluorine can be less electronegative than the oxygen. So then, yeah, it stabilizes the material. But that's just an hypothesis. But both XPS and theory verifies that indeed there should be more F terminations.
Okay, and a question about the end of the slides, the MOXCY monolayer.
Sorry, once again?
The structure where you have the what looks like a honeycomb structure.
Yeah.
Okay, somebody's asking, can you please give more details about the structure of this MOXCY?
Aha, you mean on the last image? Well, unfortunately, I cannot, because it's work very much in progress. We were hoping to have all the pieces in the puzzles resolved by now, but I think I'm not alone in saying that many projects have been influenced by the current global situation.
Yeah, you can say that again.
Yes.
Very good. That's, I think we are out of time. So thank you again very much for your wonderful talk. And
Thank you.
Yeah, and hopefully we will see you in person next year here in Philadelphia.
Absolutely.
All right, thank you.
Thank you.
Okay, so now, I don't know if I'm still live, but so in this 5 minute, yeah, okay, so we have a 5-minute break, and we'll start again at 9:30. All right, thank you very much. Welcome back. I'm your moderator, Michelle Barsoum, professor here. So our second keynote speaker for this session is a good friend of mine, Dr. Qing Huang, who's a professor at Ningbo Institute of Materials Technology and Engineering and Chinese Academy of Sciences in Ningbo in China. And with that, I, again, thank you very much for participating, and it's all yours.
Okay. Let me see. Full screen. Okay. So, can you hear me? So, hello everyone. So, my name is Qing Huang from Chinese Academy of Science. So, today, very glad to join this event to celebrate the 10-year anniversary of MXenes. So, today, my presentation will focus on the exploration of novel max physics and MXenes through a molten salt approach. So you can see from my cover image that show a terrace mountain that mimic the max phase morphologies. So I think it's from nature. So my talk will have 4 sections. The first one is the background. So why our group do some work on the max phase and MXenes. And so I will also introduce a unique method to synthesize these materials. And I will also introduce a method to predict some novel structure and how to find these max phases that never been observed. And finally, I will have a brief perspective remark on the future of these models materials. So now we know that the nuclear industry is facing a game-changing moment. The structural materials have to be more tolerant to harsh erosion, high working temperature, and heavy irradiation damage. So that's the reason we should find a new structural materials to replace our traditional cladding materials. Here is an example. So in the 4th generation reactors, there is a thorium molten salt reactor. You will see that it works in very high temperature, around 600 to 1000 centigrade, much higher than our normally working temperature is reactors. And more especially, it will use fluoride melt, so the erosion in the structural alloy will be very hard. So that's the reason we should find a suitable structural materials for the next generation reactors. Now, silicon carbide fiber, reinforced silicon carbide composite, is one of promising candidate material for fuel cladding. However, neutral radiation induced volume swelling always happened within the multi-phase systems due to the difference in crystallinity of silicon carbide fiber, internal, and matrix. So swelling mismatch among them lead to enormous cracks, which is the reason of a drop of strength as well as thermal conductivity of neutron irradiations. So our problem is that can we find new candidate for this internal to resolve this serious problem. Now it's time to MXenes. MXenes have very special properties, combined metals and ceramics. So here I need some basic properties and date that show its importance. Of course, you can get more information from this book written by Professor Michel Bachum. And it tells us that this material is very hard, stiff, tough, and conductive. The very important thing is that it can anti-corrosion and anti-oxidation. So it's a perfect candidate materials for the next generation nuclear materials. Before we employ MXenes in nuclear structural materials, some fundamental evaluation should be done to know their damage tolerance and neutral irradiations. MXenes is a big family, we know that. So we want to know which family member is the best candidate. So in the last 10 years, I work with our colleagues in Peking University, Professor Yugang Wang and Jianmin Xue. And we found that there are several crucial factors contribute the damage tolerance, such as the bonding strength in MX sublayers, anti-side defect formation energy of M and A interaction, and the phase transition from the FCC to BCC of the carbide internals. So here you will see three typical MX phases on the heavy energy air bombardment. Obviously, titanium aluminum carbide outperforms the chromium aluminum carbide. So that means we should know in detail which contribute the tolerant figures for the future application in the nuclear environment. So regarding on the coating on fibers in composite that we just mentioned, that to resolve the mismatch between them, there is a larger technical challenge for the formation of MXenes internal. So because MXenes contain transitional metals, it have very high melting point. So the traditional chemical weapon deposition technique is not acceptable. Here we adopt molten salt deposition technique to realize the MXenes coating at low temperature. By the way, we should be very careful to control the nucleation of the MXenes, but suppress the fast growth in the outer of the fibers. Otherwise, in the fibers have low chance to be coated by the MXenes. So you will soon find out that these molten salt reaction experiment largely end up our knowledge to synthesize novel MXenes and MXenes. Here we show some experiment results that we on the 3 meg electron volt silicon ions at high temperature and to a very high dose irradiation. So you can see there's no crack between the silicon carbide matrix and the MXenes internals. That shows a very promising internal candidate for these special materials to resolve the swelling mismatch during nuclear material applications. But here I should note that we only use ion bombardment to simulate the neutron irradiations. So further work should be done to re-evaluate these candidate materials in the real circumstances. Now we can get some information from this periodical element table. We know that if we can control the neutron absorption capacity of max phase by choosing an element with different neutron mass absorptions. If we choose no absorption elements, that means very high economy in the fellow reactors. But on the other hand, if we choose a high absorption element, but its structure is very stable, that should provide a good neutron shielding or protection structure materials. So we do that there is a trade-off between the structural stability and the neutron economies should be considered in detail. So how to choose this element in the fellow max phases when we want to employ it in the fellow applications? So here we know that not all elements can be involved in max phases. From the classic version of the element distribution in periodic table, M elements are early transition elements. A element contained the group 13 to 14, and X is carbon or nitrogen. Here I choose version 2 that just mentioned in a review work by Bashum, that there is some important findings in recent years. You can see here the iridium and the golden element at MSET have been realized, that reported by Dr. Per Eklund and their colleagues, and some lanthanide element at M-site in the I-max phase, as Johanna Rosen just introduced. So now I will only introduce the finding of our some new ternary max phase discovered in our group. Here I should say that if we can control the A element, so there are some changes between the M and A element. For example, the interaction between the titanium and the A element change from the zinc to copper, then to arrow. You will see that the interaction will change from the d electrons, d orbit electrons with p electrons, and also to the s electron, and further to the d electron. So I think the properties will totally change. But how to make these new max phases? So we make some simulation on the phase diagram. Here we see that for the zinc max phase, it only step at very low temperature, around 550 centigrade. But for the experiment synthesis, at low temperature, the kinetic process is very low. So that's the reason we cannot easily get these new max phases. Here we find out a new synthesis approach to make these new max phases. So we can take advantage of the weak interaction between the M element and the A element. And now the joint force between them is the redox reaction between the aluminum and the zinc cations, cation. And the evaporation of aluminum chloride realize the replacement. Then we can get to know that zinc and the aluminum binary phase diagram, that eutectic point of this alloy is pretty low. That means that the zinc atoms can diffuse into the A nail very easily. Most important thing is that this reaction approach will avoid the competing phase of the titanium zinc alloy. So that's the reason we can use this replacement approach to make some new max phases. Here I show some characterization of these new materials, but be careful is that because we use the precursor, that the crystal structure have low change, so we cannot see any geometrical changes in the XRD spectrums and also the morphologies. But thanks to the excited work by the Dr. Jun Lu in Linköping University, we use that STEM technique, and finally we observed that the totally replacement of the aluminum by these zinc atoms. So we can also use several other max phase precursors, and for example, we can use 211 max phase, and we can use nitrate max phase as a precursor. So there's no doubt that we got some similar results that to get some new max phases. Here I show the Here I show some example to make replacement by the copper atoms. So we can see from the phase diagram calculations that the copper ternary max phase is no way to exist, because the competing phases of these alloys can much more competitive. But if we can use the same strategy to make a replacement between the copper atoms to the aluminous, we finally can synthesize these new max phases contain the copper in the anneal. And I think these new phases may show some new properties. Here I show that if we put these max phases powder into the peroxide solutions, the copper max phases may act as a catalyst to decompose this peroxide into oxygens. But if you use the traditional max phases, there's no such reaction. So it can be a single atom catalyst in our new max phases. I think it should have more chemical study in these new materials. And I think it's by accident that we changed the molten salt system, that we use barely the zinc chloride as a melt. And we found that there is the evolution from the zinc ternary max phase into the chloride terminated MXenes. So it can be a very green chemistry approach to make the MXenes. Here we use the STEM technique to clearly see that all the terminals have been transferred into the chloride groups. And this work by Dr. Person is very wonderful examination on these new MXenes. And we finally observe that this chlorine group is very stable, up to even 750 centigrades. So it may provide a new platform for the further energy storage applications. Here we can generalize this molten salt approach to make MXenes, because we know there's many max phase family members. So in these mapping images, so you will see that if we can choose proper Lewis acid melt, so we can meet the edge on almost all max phases, whatever the A element. So I think it's a guidance for the choosing of the suitable Lewis acid melt. So here we have a collaboration with Professor Patrick Simon and Dr. Ning, and we found through this approach, the final product of MXenes should very promise energy storage in long accurate battery systems. So I will not discuss some detail about it here. And we can choose some other melt that we change the anion systems. So here I show if we use a bromium melt and also iridium melt, so we can change the terminals of the final MXene product. And moreover, we can combine these groups together, that in these MXenes we can see all these halogenate MXenes contain chloride, bromine, and iridiums. So what's the advantage of these new MXenes? Here we try the test in a zinc-ion battery with the help of Professor Zhi. And we see that from this figure A that there's no electrochemical activity in the traditional MXenes, including the chloride one. But for the iridium one and the bromine one, that you can observe some redox peaks here. And this redox of the terminals can contribute the energy density and their capacities. So that means there's not work on the surface termination on the max phase to change their properties. So here is some new work published in Science. So here you see that this shows that we can further make some replacement on the anion on this bromine MXenes to make some chocogen terminated MXenes. And this work even shows that some MXenes show superconductivity. I think it's largely expounds the application of these MXene materials. Now I should say something about the new max phase. and how to synthesize some and how to predict some new max species. I think it's important to get some new MXenes because it's an important precursor to get it in. And for the experiment scientists, that we always think about some basic parameters of element, such as the size and the weight and their valence electrons. Can we have a simple concept that help us to predict some new max species? So here we get some information, some basic information from this periodic table. And you can see that there are atom size and there's electron concentrations. So we can use these basic informations to predict some new max species for our further studies. So this work by Dr. Zhang Yiming, and we use structure mapping to provide the guiding principles in the search of new max species. And we actually predict that, for example, the iron, cobalt, nickel can occupy the acid in the max phase, and it's stable. So here I show our previous results that in the vanadium max phases, we observed some magnetic elements in the acid. So here we show the iron, cobalt, nickel, and magnetic in the anneal. So here is my imagination is that if we can control some magnetic elements in the anneal, maybe we can use this max phases as spin Chordicus materials. That may be our future work to try it. So I want to make a simple conclusion of our synthesis methodologies, that if we use molten salt as use their Lewis acid properties, if the Lewis acid is very weak, we could get some novel max phases. So that means we can change the A element into zinc, copper, iron. So it naturally can broaden the properties of these molecules materials. And if we use a stronger melt, we can easily etch out the A element and got some interesting MXenes. And more important is that we can control the terminus of these new formed MXenes. So here I have a friendly advice that don't throw out every trash when your student fail to obtain the MXenes, because sometimes you may find out some valuable max phases in your table. That's a lesson learned from the discovery of MXenes when max phase failed to resist the HF corrosion in 2010. So I want to give a very short perspective remark that we know that max phase have been studied and discovered almost half centuries ago. So, but in the last decade, we see fast growth in this field that due to the discovery of the MXenes 10 years ago. Here we see some new tendencies of the discovery of some MXenes itself. I believe that there is very large spaces in the next decades that for these spatial materials. And I here should see that there is a bright future for this MXenes and MXene materials for its diversity in the element and also in their terminal groups. Also, we may find some novel functionalities such as energy storage, EMI, catalyst, bio. So I think we can name from the Professor Yuri Gorch's review that the rise of MXenes give some dream for the future. So we will have a conference in Ningbo, China in the October this year. But for this COVID-19 pandemic, I'm sorry we cannot invite all of you to join this conference, but we will have visual tapes to share some report and speech with you guys. So finally, I should say happy birthday to you, MXenes, for these 10 years journeys. And we hope to see more exciting moments in the next decades. Thank you very much.
Yes, thank you, Xing, for this really fascinating talk. I really enjoyed it. And I think this, as this science paper shows, you opened up a fantastic avenue to not only create new max phases, but also MXenes. So we have some time for a few questions. One of them says, basically, are these salt-etched MXenes hydrophilic? And what type of charge is attached to them?
I'm not sure which charges I'm not measure zeta potential measurement, but yes, it's good question. Yes, it's good question. So,
are they hydrophilic?
It's hard to see that because during our synthesis process, we always had to remove the salt after the synthesis. That means some oxygen groups, such as hydroxyl, will attach on the surface. Okay. So that means the surface state will change when we do the further purify step. Yeah.
All right. Another question is, what is the stability of these MXenes?
Stabilities. I think this stability should be enhanced. Should be enhanced. My student once tell me that it keep in the air for a long time, several months, and the structure is very stable. And I think it form a buffer layer to stop the penetration of oxygens into the into the MXenes. But we should have very detailed evaluation for this stability of these new MXenes. Yeah.
Yeah. Okay. We have time for one last question, which is related to this one, which is, what is the stability in water?
In water?
Yeah.
So we should have a careful measurement. So I mean that in the pure water is okay, but yes, if I think it should be attacked by the oxygen. So I think it's better to keep yes. I think so. I think we should do something to evaluate the stabilities. Yeah. So it's a good question for the real applications. It's always a problem for all MXenes.
Yes, okay, so now we're out of time. Again, I'd like to thank you again very much.
Thank you, Michelle.
Yeah, thank you, Ching.
See you.
See you. And we will now take a 5-minute break. So we'll come back at 10:51 to the last talk for today by my good friend Garrett Tucker.
So you're looking at a compound that we've created here at Drexel called MXene. We discovered it in 2011, but have recently learned how to make it behave like conductive clay. This stuff has the potential to replace the electrode material found in supercapacitors and even batteries. In the past, to create pure MXene films, you'd have to etch max phase with hydrofluoric acid, wash it, intercalate it with dimethyl sulfoxide, sonicate it, centrifuge it, and filter it. We've managed to cut the process down to just the etching step. Now, we simply react max phase with an etchant made from much safer acid and a salt, and after washing, we're left with a clay-like material that we can shape any way that we want, even rolling it out into a film. After drying, it's highly conductive. Not only is the process easier and safer, but electrodes that took us only 5 minutes to roll out have shown a 200% increase in capacitance over our previous reports. Sometimes the simplest ways are the best, and it's one of the many great things only happening at Drexel.
Okay. The next, I hope you can hear me. All right. Yes, I got the yes. So the next talk is by Professor Garrett Tucker. Like I said, he's a good friend of mine, and he used to be at Drexel here a few years ago, and that's how I got to know him. And we are working very closely together on replications and other interesting ideas. And so without much further ado, it's all yours, Garrett.
All right, thank you, Michelle. All right. All right, so I want to take a moment first to thank Professor Gagotsi and Barsoom for putting together this this event this week, and for the very generous invitation to take part in this and to share with everybody the work that we've been doing over the last couple of years in this field. So my talk today, the aim of it is to go a little bit different direction in the sense that we want to start to probe the fundamental mechanical properties of MXenes, and specifically looking at new developments and new approaches, let's say, with atomistic modeling and computational tools in that vein. So to start out, I'd like to thank some collaborators over the past couple years that we've been working with on this. The first one is my PhD student, Gabriel Plummer, shown here to the top here, and then Professor Gagotsi and Professor Anasori, who need no invitation or no introduction, obviously, in this community here. The work that we're presenting today has been performed using a few different facilities over the years. As Michelle mentioned, prior to my current position at Colorado School of Mines, I was at Drexel. So this actually started using the Drexel University Research Computing Facility. And then as we moved over to Mines, we used facilities over here. Funding, obviously, through this is very important to acknowledge. And Gabriel has been supported financially through a Course Tech Graduate Fellowship for this work. And we also have a partial support through a National Science Foundation grant as well. Okay, so to start, I wanted to start with this, and I hope that Yuri doesn't mind me sharing a slide of his, in a sense that it outlines a lot of numerous remaining challenges in MXenes to pursue. And so just over a year and a half ago, Yuri gave a terrific distinguished seminar out here at the Colorado School of Mines, obviously explaining all the terrific things about MXenes and stimulating a lot of discussion and interest in MXenes. And so he concluded his talk with this list of bullet points here. And obviously this is by no means a full list, but it obviously includes some of the future direction areas here. And we're interested in the fundamental mechanical properties of MXenes. There were kind of three areas here that I thought kind of stood out to us. And this is in regard to, moving beyond kind of these traditional MXenes, which we've heard a lot of talk already today on. Some fascinating work already going on and published in this area. In addition to defects, which Professor Rosen did a great job discussing that earlier this morning. Considering defects, what's their influence on properties and control those. And then lastly, when we think about exploring MXenes in other materials and introducing them into composite materials, we really need to think about some of those fundamental properties of those MXenes to optimize that integration. And so obviously here, we want to focus on the mechanical properties. And I would say that these fundamental mechanical properties will be paramount. So in addition to the vast work that's been done using density functional theory and ab initio calculations on mechanical properties, there actually are still some other things to be done, which I'll be talking about today. So the overview and objective for this talk today I'm hoping to cover is that we want to cover some newly developed interatomic potentials. And I'll talk about why we care about these later on. But in a sense, we want to develop energy functionals that we can fit to data and then basically extend out our simulations to get to the place where we can start to model and simulate tens of thousands, millions, tens of millions of atoms do these, to probe the fundamental mechanical properties. The second thing is to demonstrate how these atomistic models and simulations can be used to provide valuable insight, such as strength and deformation. And then lastly, discuss some potential avenues to further extend these new developments and capabilities of computational modeling, and hopefully with the eye toward better connecting with the novel testing and characterization efforts that are going on around the world right now in regard to MXenes. All right, so to motivate this, shown here are two different plots looking at the in-plane elastic constant, or the elastic modulus, shown on the left here, where this is a computational study comparing MXenes to their max parent material. And then shown on the right is a comparison of experimental nanomechanical testing, looking at the comparison of titanium-3 carbon-2 with other 2D materials. And what we see is that both modeling and experiments suggest that that MXenes have excellent fundamental mechanical properties, both in comparison to their parent max phases and in addition to, or relative to, other 2D materials as well. And I think this plot on the right is even more telling when you think about, and this has actually been discussed a little bit today, is that the way that we actually process these materials. And in a sense, do we actually do exfoliation? Do we do solution process? And when you start to think about those things in the including of termination groups, or BEAR, I think the comparison in regard to mechanical properties is very clear of MXenes compared to other 2D materials. And so when we take a kind of a step out, and I know this image has been used a number of times over the past couple of years by both Yuri and Babak, but looking at kind of this whole picture of all the applications and all the technologies where MXenes can benefit, what we see is that the structural component of this, focusing on fundamental mechanical properties and these composites, progress in this area has been relatively slow compared to a lot of these other areas, and there's a lot of good reasons for that, but that doesn't necessarily mean that we need to ignore that. So that's what we're going to focus on here today. And so we have to bring up some of the challenges and limitations, both experimentally and computationally, when we start to look at the mechanical properties of MXenes. And so shown to the top right here is some images here looking at some of the challenges working with monolayers. So if we were to, basically deposit, peel off these monolayers of MXenes and test them mechanically, there are challenges with doing that. Shown on the bottom, there's been a lot of, like I said, terrific work using DFT to look at the mechanical properties such as elastic constants using DFT, but there still are limitations there as well. And so we have to think about those and consider those when we think about the bigger issue of understanding broader mechanical properties of MXenes. Like I said before, there's no way that we can sufficiently summarize all the work, all the great work that's been done with DFT over the years, but it really has provided a lot of valuable information on the elastic properties of pristine monolayers for the most part. And so shown on the left here are both in-plane and out-of-plane moduli, comparing calculations of MXenes compared to other common 2D materials which have been studied. In the middle here, we can see the effective temperature on elastic constants, specifically looking in here, the titanium carbon based MXenes with oxygen terminations. And then on the right, what's the influence of surface terminations in regard to the stress strain response of MXenes? And so shown here, we can see that there is an influence of these surface terminations on the mechanical properties of these MXenes. But what we really need to think about here when you search the literature, and what we need to understand is that real MXenes are not pristine, that we have these surface terminations as we've seen today, and it could be a complex distribution of terminations. It could be not one type, it could be multiple types, and they're not fully elastic either. We see MXenes that break, we see the failure of those, and so we actually have to think about that as well. And so kind of in that vein of thinking, here's some work where folks have looked at non-equilibrium defect concentrations, very much in line with what was talked about earlier. by Professor Rosen, looking at vacancies and looking at the correlation of defect concentrations with how the material is actually processed. Once again, reiterating the point in the middle here that there are non-uniform surface termination distributions. It might not just be one type, there could be many types. And we have to think about that and consider that when we come up with a strategy to probe these fundamental mechanical properties. And then lastly on the right, which is much more aligned with motivating the talk here today, is what we see complex fracture mechanisms when we mechanically test these MXene monolayers. And there's been some terrific work done here by Liptov and co-workers over the past couple of years in this area. And so what you think about here is that if we're going to use computational tools to study mechanical properties, the simulations need to be scaled up beyond a few hundred or even a few thousand atoms. And so atomistic modeling, and this is a computational tool that it basically relies on solving Newton's equation of motion and employing an interatomic potential to derive those forces and dynamics of the system. Atomistic modeling might provide a solution here. And so shown here on the bottom left, or actually on this slide, we pulled out two different examples of two different types of interatomic potentials, which have been mostly used over the past few years. One is the hybridized potential shown here in the left side, and this has been really well implemented to look at some of the mechanical properties, thermal properties of MXenes. And one of the drawbacks here is, at least not yet to our knowing, no surface terminations have been included in some of these potentials. We could be wrong about that, but I think that's one area that is a consistent theme here that we need to address. On the right here is a reaction force field potential. These have been used very successfully to look at intercalation dynamics and growth mechanisms of different types of clusters and different types of MXenes. But here too, there are drawbacks. It can be computationally very expensive to run, orders of magnitude slower than other potentials. And if we were to think about studying a monolayer size, we're usually limited to in the 10 to 50 nanometer range with a reasonable amount of computational resource. So continuing that, we actually did this a few years back with Professor Gagotsi and Professor Anasori. My student, when he was a master's student at Drexel, started this, where we actually basically constructed these monolayer MXenes. These are bare to start, and we simulated nano indentation of these MXenes to hopefully mimic very, very small scale experiments, which we couldn't reach the true length scale, but we can actually approximate that with this length scale. Here, what we see is a 25 nanometer diameter monolayer of Ti3C2. And like I said, we started without surface terminations, and then using reacts, we were able to add in various surface terminations. And we indented these. We simulated the nano indentation process as shown here on the right up until the point of fracture. And so you see this top view and a side view of the simulation continuing, where we can start to see, we color the atoms here according to their shear strain relative to the initial undeformed state. And you can start to see that we get very complex deformation before fracture and then during fracture as well, or during the breakage of the monolayer. And because atomistic modeling, we have all this information from the atoms, we can start to really explore that behavior in a much more detailed point of view. As long as we believe the potential, as long as we believe that potential is giving us reliable information there. So after we run these simulations, we get a force displacement curve out of that, and then we can fit that to a known model for these 2D materials, which gives us the 2D elastic constant. And so shown here in the middle is the simulation data for Ti3C2, bare in this case, and we see that it approaches about 400 Newton per meter, whereas an experiment from Liptov and co-workers, we can see that the 2D in-plane modulus is about 318. And so the question obviously is why do we see such a difference, a significant disagreement between the resulting in-plane mechanical properties between simulation experiment? And there's a lot of reasons for that. But one of the things that we thought, at least in this paper that was published last year, was that defects significantly influence those properties, especially the fracture. And so shown here on the left, we took a different approach where we actually then started to induce vacancies on both the titanium site and the carbon site through the monolayer. And as we increase the concentration, what you start to see is that in-plane elastic modulus starts to decrease. And if you were to normalize that value by the experimentally measured value, we actually come down and we start to agree with that at higher defect concentrations. Once again, kind of supporting this notion that these MXene monolayers are not pristine. They probably do have these point defects in them, and we can start to probe that information with atomistic modeling. And so shown here in the middle is a snapshot of when the MXene starts to break, both with and without defects. And you can see that there obviously is a very strong dependence on the fracture characteristics when we consider point defects in that MXene monolayer. And so after this study, we thought about future directions and limitations of this study. And so obviously we need to think about various MXene chemistries, which has been very much in the theme of today's talks, role of surface terminations. And then maybe these last two I think are the most important and motivate the second half of my talk today, is that we need to think about monolayer size. Here we're talking about 25 nanometer diameter sizes, where experimentally we were in the hundreds of nanometers. And so to do that, we came to the conclusion we have to develop a new interatomic potential with a focus on the mechanics. And that leads us to our current work that we're doing. So here we turn to bond order potentials. And so earlier I talked about these hybridized potentials and reaction force field potentials. And one of the reasons we turn to bond order potentials is they are both flexible and scalable. And they're highly flexible in the sense that we can mimic or represent and model different types of bonding environments, such as covalent, metallic, and ionic covalent bonds. These have been successfully done over the years. And one of the things we liked about this was the energy functional for describing the potential between the atoms is relatively simple, in the sense that there are basically these four different aspects of the functional. There's a cutoff function, there's a cutoff term, there's a repulsive pairwise term, the attractive pairwise term, and then this bond order term, which gives us a lot of the tunability in regard to the energy functional. And so if we were to think about the titanium carbon-based MXenes, which we'll be talking about today, the number of parameters we have to optimize to. We have 11 per elemental interaction and then 14 for each binary interaction. So for this particular system, it gives us 36 parameters in total. We have to numerically optimize to a set of target data. And in our case, that target data is both experimental data and a lot of DFT data as well. So when we develop this potential, we optimize it, we have to test it. And so what we did here is we took both the elastic and structural properties and various properties of point defects. And so shown here are three different stoichiometries of titanium carbide MXenes, the 2.1, the 3.2, and the 4.3, comparing published DFT values and the bond order potential calculated values. And as you can see across the board, we actually get very nice agreement in all three chemistries, and down through the table looking at a bunch of different elastic and structural properties, looking at the elastic constants, the lattice parameters, cohesive energy, and then down at the bottom, various point defect sites within the MXenes. So we're fairly confident, at least in regard to the available data we have from published literature, that this bond order potential we have now does a good job for this titanium carbon system, and it does a good job for all three stoichiometries. And so if we look at kind of an overview schematic of this new potential, it has high accuracy for all of them. As you've shown here, we have the percent error on the vertical axis and then various material properties on the horizontal or x-axis. And both these structural and elastic properties are all predicted to be within about 5% of those target values we get from density functional theory. And just to kind of reiterate here, this is one potential for all three systems. So it's not one potential for each. We have one potential that actually does all of them. And that's actually a very hard thing to do. And so in summary, for this potential part, we thought, bond order potentials, they can successfully model MXenes, and all three bear, for the time being, titanium carbon structures. And the surface terminations can now be added in with additional DFT data that we can get. And this is actually in progress right now. We are actually in the process of doing this. We'll have various surface terminations in this potential. And now that the numerical optimization algorithm is completed, it's actually very easy to tune it for a specific type of systems that we're interested in doing. And then lastly, preliminary tests show that the model can easily be extended to other chemistries, such as the nitrides, other types of M-based elements or multi-M elements, provided that we have that DFT and experimental data available to us to optimize to. And that too, we are actually in the process of doing that and gathering that information from colleagues. So now that we have this potential developed for at least the bare MXenes, we need to use it in a larger atomistic model to probe these fundamental mechanical properties. And so what we're gonna do is we're gonna take a couple different examples here where we can probe the in-plane and out-of-plane mechanical properties, in addition to looking at the fracture of the MXenes. And this kind of is complementary and builds upon some previous work in this area as well by others. So we're gonna show you that here. So the first thing we wanna do is we wanna use nanoindentation. And this basically takes our initial study we did and just scales it up. And like I said before, the limitation was computational efficiency with the reaction force field potential. And because we can only get to a certain size. And now we can get into the hundreds of nanometer size and very much approaching what is experimentally done as well. And so we did this for all three of our titanium carbide systems. And then we did this at 10K. The simulation was performed at 10K, and we continue this until fracture occurs. And then out of the simulation, we get force displacement data, and we have all of the information for every single atom. This includes positions of the atoms, the structure of the atoms, the stress and strain of the atoms, in addition to some kinematic information that we can calculate in a post-processing way. And what we're hoping to do here is to find out the trends in elastic modulus and the breaking strength of these MXenes, looking at various variables along the way. So shown here is a movie, and I don't know, hopefully this comes through over the Zoom site, but this is a Ti2C monolayer. And once again, this is 100 nanometers using this bond order potential we developed. And this is no surface terminations. And I don't know if it's actually showing up, but basically we're taking that simulated nanoindenter and we're going right down in the middle of the monolayer until it breaks. And we can capture all of that dynamics in a simulation and start to look at the output data and look at those trends. So we use LAMP software package for the simulation and Obito software for the visualization. And so if you were to take a snapshot more or less of the end part, and this specific one is for a Ti3C2 monolayer. Once again, the diameter is 100 nanometers. And we compare the simulation to experiment. And we understand the length scales are different here, but we see qualitatively similar fracture and anisotropy and behavior here. So this gives us a little bit of confidence and motivation to keep going. And like I said, we want to add in these surface terminations, which we're doing. But now we have the numerical framework, we can scale this up into much larger systems to really get after and kind of connect better with those experimental studies. So from that data, we can actually then also output the in-plane modulus. And so shown on the left here is the modulus versus the monolayer diameter. And as you increase the monolayer diameter down from tens of nanometers up into 100 and beyond, what we start to see is we approach values for that in-plane modulus for all three systems. And shown on the right is a table comparing the calculated 2D modulus value for the three different systems, both at the 100 nanometer size that we simulated, in addition to the functional fit as you increase the diameter out to infinity. And we compare these to both the experimentally measured values of graphene and Ti3C2 with termination groups. And what you can see here, obviously, is that the in-plane modulus values are very significant. They're significantly lower than experiment, but we know that those surface terminations have been shown to stiffen the monolayers. So we have to think about that too. Now, if we move on to breakage strength, we can do the same thing for breakage strength here. And if you look at the chart on the right, do the same thing. What we end up seeing is that our simulated calculated values are actually much significantly higher than experiments. And that is actually likely due to the absence of these defects in the simulations that we talked about earlier. The next thing we want to do is look at the out-of-plane elastic properties such as bending. And so here we just took one of these MXenes and bent it at different curvature values and calculated the strain energy for those, and then fit that to a continuum function to calculate that out-of-plane elastic, that bending modulus value D. And if we were to do that for different systems, what we end up seeing here is that the 3 different MXene chemistries that we looked at all have much higher bending modulus values than both graphene and aluminum disulfide. And when we actually plot these values on a curve, we actually see that it roughly follows the cubic dependence on the thickness of the MXene, which it should. But to verify that actually was a very important step here. So the next thing we want to do is we wanted to look at in-plane strength and fracture, moving away from nano-notation and thinking about uniaxial tension. Now, like I said, this is kind of repeating, but builds on some previous work that's been done in the field as well. So here we use a 50 nanometer by 50 nanometer MXene sheet and pull on it until we get fracture. And here too, we want to output the role of different things on elastic modulus and the breaking strength or fracture strength of the MXene. And so when we do that, here's the stress strain data for those studies. We have all 3 of our titanium carbide MXene systems plotted here. And then we did it at 2 different in-plane orientations, both the zigzag and the armchair orientations. And you can see there is a dependence, obviously on the stoichiometry, but also on the orientation at which we pull in plane in the MXene itself, both on the strength of it and the strain at which fracture occurs too. And these data are very important, but really we want to understand some of those fundamental mechanisms which lead to fracture. And so here is actually a comparison of the modulus, the strain to failure, and the tensile strength from those plots, comparing the different MXene systems and the different orientations. And I think a really valuable piece of information that came out of this is that what we see is the MXenes, at least in this case, the bare MXenes, are elastically isotropic, but plastically anisotropic. And that's a very important thing to do or to understand. And that the modulus values that we calculate from these uniaxial tests agree well with the nano-indentation results we did earlier. So we're getting very consistent modulus values. And now we're actually getting a trend in regard to the tensile strength of these materials. So here's a movie of the armchair configuration for TI2C. And I hope this works over the Zoom. But what you see is we're pulling from both left and right directions outward. And then eventually this thing will break. Yeah, so we can see the breakage right here. And so if we were to go back, we can actually start to isolate some of these states prior to breakage, because we have all of this information, and we can start to understand those fundamental mechanisms which lead to fracture. But you can see here, right here, we get a clean breakage perpendicular to the direction at which we pull on this MXene, which could be logical in a way. But here now we do the zigzag direction, and this is another TI2C simulation. And I'm going to speed it up here to where it breaks. And here we get a completely different type of fracture path. So not only the in-plane values that we measured earlier, calculated values earlier, different, but the behavior of fracture in plane is completely different as we change the orientation. And here's kind of a comparison looking at the 3 different stoichiometries, comparing armchair and zigzag. And one of the consistent themes here is that we see this preferred failure along the zigzag directions. And like I said before, these are pristine, bare MXenes right now. Now adding surface terminations and these defect configurations are underway right now. And so we can't comment on those results, but they do obviously influence the fracture behavior. So in conclusion, some of the fundamental mechanical properties of MXenes can certainly be probed with atomistic modeling, in addition to kind of building upon all of the phenomenal work that's been done using DFT calculations over the past few years. And we believe that developing new isotropic potentials potentially are a way to actually do this, where we can reach larger monolayer sizes. We can look at bending moduli calculations as we showed. And then lastly, elastically isotropic, but plastically anisotropic was one of the themes that we actually saw when we started to perform these mechanical tests of these monolayer sheets. And then lastly, emerging experimental and computational data show the importance of considering size, chemistry, surface terminations, order, disorder, as we've been hearing about earlier today. We really have to think about all these things when we develop a deeper understanding of the strength and deformation behavior of MXenes. But one of the things is like I mentioned before, developing these interatomic potentials. Doing this first step is very important. Adding in surface terminations and point defects are a very straightforward extension now to do that once the potential has actually been developed. So lastly, once again, I want to acknowledge the My collaborators over the past couple of years, my PhD student Gabriel Plummer, Professor Gregozzi, and Professor Anasori. And then lastly, the funding agencies, once again, the funding sources of the Course Tech Fellowship for Gabe and an NSF grant as well. And with that, I'll say thank you, and I'll take any questions.
Okay, can you hear me?
Yeah.
Yeah, okay, great. Thank you, Garrett, for a really great talk. I'm familiar with your work you're doing on the max phases. And this is really great. So we have some time for a few questions, and I will start. One question: what experimental data did you use to parameterize your BO potential, or do you use DFT data for that?
Mostly DFT data. Yeah, that's a great question, and the reason is because in regard to those properties we're looking to fit the potential to, that's where the majority of the data is at.
Okay. The other question is, let's go back to here. So Vadim has a question. He says, while it's not surprising, this has to do with the beginning of your talk, that auction termination can change mechanical behavior of MXenes compared to bare ones. Can you give an explanation why the hydrogen terminated changes stress strain compared to the bare MXene?
If that's in reference to the article we cited, I can't right off the top of my head. Okay. Yeah, you'd have to reference that or kind of go to that paper to find out what they found.
So the other question is where the Reacts FF potential trained for mechanical properties?
I believe there were some mechanical properties in there, but not to the extent that we were actually interested in. Mm-hmm. Yeah, that's a great question. And that too, and that was kind of a reading or a consistent theme, is you have to think about the right data to fit to as well. And it has to be complete.
Okay, another good question here is how the stochastic behavior was implemented in numerical simulation to predict fracture patterns. I presume this question relates to the vacancies, when you have vacancies in there, I suspect, because the stuff you showed at the end, that was perfect pristine, right?
Yep.
Okay.
Yeah, so it is a great question, and it's a very important consideration, actually. And you have to think about the distribution of those vacancies and whether you can get experimental imaging to look at the distribution of vacancies and point defects. The way that we did it is we chose a concentration and then kind of randomly distributed them out. And we did multiple instances of that to try and get a statistical sense of that. But it's a great point that has to be thought about. It's exactly right.
Okay, thank you. Is there another question, any strain rate dependency in the strength modules computed by the BO methods?
Yeah, that too is obviously a very fair point for pretty much all of molecular dynamics simulations, and there are strain rate effects. There's certain things we can do to help kind of alleviate some of that, but there are strain rate effects there too as well. That's right. And so obviously we can lower the strain rate. We can do strain rate sensitivity tests across a range. You can try and do molecular statics to do like a quasi-static approximation. But in this case, we just chose a relatively low strain rate in regard to MD, and then ran the simulation and saw what we saw. But if you were to do a lot of these, even with quasi-static, you don't see large differences in regard to some of those properties. But the qualitative trends are still similar.
All right. So another question is, can you comment on why these MXenes are elastic isotropic, plastically anisotropic? Any physical mechanism?
Yeah.
3D material, ductile plastic deformation is associated with siltation or the deformation of to be MXene?
Yeah, it's a great question and very much in tune with obviously some of the work that we're doing with Professor Barsoom right now in Max. I hate to comment it before we actually get a complete study on that done, but yeah, it has to do with those fundamental mechanisms inside the MXenes, which lead to bond breakage. And there is anisotropy there that we're actually hoping to quantify exactly. Yeah, that's a great point.
All right. I think the last one here, how does the number of layers affect the plastic behavior during failure, or is failure mostly based on armchair versus zigzag orientation?
Yeah, that too, we haven't done that. So I would hate to comment. Obviously, I'm sure there's a dependence on the number of layers, but without actually performing those studies, I'd hate to comment one way or the other on that. But it's a really nice avenue for future work as well.
Okay, I think unfortunately we're out of time. There's a lot of other questions, so maybe we'll invite you next year so we can answer some of these questions.
Right.
Anyway, so before I finish, I want to thank Garrett again for a great talk. And I want to as importantly, I want to thank all the speakers for taking part in today's sessions. All the talks were really world-class, top-notch. Now, for tomorrow, I hope that you will tune in. Tomorrow's topic is electronic and medical applications, MXenes. We will also be sending you a survey, and if you by email. So if you could really give us feedback, that would be great. Again, we're doing this for the first time, and the more information we get, the better we can do the next time. All right, so there's also, we invite you to a poster session. A link was sent by text, so please double check on that. There are posters. Okay, so the last thing I want to do is, for those of you who still are interested, I just want to go and share my screen with you guys, maybe at this time with so now can you see my screen? And the problem is when I look at the screen, I do not know, I can't tell, because I don't see the chat box, whether it's working or not. Let me back up, stop sharing. So do you see my screen? Did you see my screen a second ago? Yes, okay, so whatever bug we had seems to have gone away. So let's share this again. So, and we go to full screen, and I promise I'm not going through the whole talk. I just want to show you. Luckily, my talk was mostly thanking people, that came through. So anyway, so this is, as you know, the MXene, the MXene transformation that we've been hearing a lot about today. And this is the picture. I really like this one. So you take a 312 particle and put in HF for 2 hours, and you go from 3D to 2D. It really is magical. And this was the first paper. We made the cover that year, and this advanced materials paper was our first. This was, again, discovery made 10 years ago, publication 9 years ago. And this paper has been cited, I think, almost 2,000 times. And then I went through these, and again, these, luckily for me, were all words, so they came through. Yeah, these all came through. So that, then this is the one I want to show you that is really remarkable. So the total number of publications is over 3,000. Again, I also read those numbers, so that was not too bad. Total citations was up to 90,000, H-index 137. And again, if you go here, this has doubled since 2011. This has doubled, roughly doubled every year. The same with the citations per year. So this is a very hot topic and obviously attracting a lot of attention. Top 100 papers are highly cited, as I said. And this is, again, unfortunately, where you needed the picture, but you get the picture, pun intended. Here we can have just a simple monatomic M. You can have disordered solid solutions, you have solid solutions, you have 5-4 that are not even on here. So now, this is the visual. So if you take the MXene periodic table, again, this is from Babak, who's a faculty now in Indiana, Purdue. And with the latest paper from the Science that last week or so, I think Babak, you can start coloring some of these. So it really is remarkable. I mean, for all intents and purposes, you can use the entire periodic table in some fashion. So that has to lead to just an amazing power and potential for designing properties. And then again, this was that was thankfully also you need a visual. You need so if you take terminations and you do the combinations, they blow up, and the future is very bright. And again, here I just want to show the picture. This is Tamer Rakhi, who did Max work, and Michael Agib and Joe and Babak and Haroon and Michael and another Michael. There's 3 Michaels here, and my son is also called Michael, so maybe I'll get him to work on MXenes. And this is Yuri's group, and again I thank Yuri and his group for really fantastic effort to get this rolling. And special thanks to Dr. Arman Mohammadi for the artwork. Again, these are the speakers, and again, this is the visuals. So these gentlemen here are all somehow related to, they're all giving talks that are somehow related to Drexel University. So obviously there was absolutely no bias when we chose these people. And thank you again. That was, we didn't need to see pictures for that. Danielle is, again, I thank you very much. And that, yeah, the program. Okay, thank you very much. And I hope to see you all tomorrow.